Okay, we're now recording. And let's talk about statics, torque, and rotational motion. So the first step, you guys should know your terms. You should know what center of gravity means, equilibrium, when things are balanced. I guess was a machine from still machine. We didn't really get in that great detail, but again, if you click on your notes, problem sets, solution keys, again, that's in Schoology. If you go to Schoology again, just click on problem sets and click on solution keys, and it's all right there. Everything you need is right there. But the one that will probably help us answer some of those questions or terms would probably be in the beginning here about equilibrium, for example, like what is meant by equilibrium, you know, the conditions you need for that, like no acceleration, tau net equals 0, or stuff on machines. We did have that discussion. We didn't really do the problems. We just had that discussion. Stability. Again, we had that discussion. Center of gravity and all that stuff. So I think there's another one here on kinematics, a bunch of equations. So it also would help to probably have all your notes in front of you for the final exam. That's always a good thing. Remember, it's open note. So yeah, so all those terms there, again. All very, very important to, you know, just kind of know what those mean. Mechanical advantage, angular velocity, angular acceleration, tangential acceleration, angular momentum, torque, inertia, rotational kinetic energy. So know your terms. Rest, it looks like it's all going to be problems to work out, which is great. There's 15 problems that can really keep us busy. Let's kind of go through each of them one by one, just to make sure they seem legitimate, because I think that does seem legit. That doesn't seem like we've really done. We could just X that out. So for number 2, you have a 1.9 kilogram hoop, rolls without slipping, which you see right there off to the right. On horizontal surface, so that center proceeds to the right with a constant linear speed of 5.4 meters per second. Its radius is 0.5 meters. What is angular momentum? So remember, we do have formulas for that. So angular momentum is right, where the heck is it? There it is. That's capital L, that's I omega. So you need omega, which is going to be V over R. So velocity equals R times omega. So omega is V over R, which we totally can do because we do have the velocity, we do have the radius. So that's going to be easy. To get to omega, it's going to be 5.4 over 0.5. So let me get my, actually my stylus hasn't been working. I think I need to buy a new one, or we're worried that it's not charging. But remember, omega is V over R, so it's going to be a little sloppy. I apologize. Your V is 5.4. Your R is 0.5. So your omega is going to be 10.8. And remember, L, that's angular momentum, is I omega. Now your I is going to be your inertia. Now, I has a lot of different formulas. They tell you this is a hoop. So we go back to our formula sheet again. For hoops, you have a hoop, and it's yeah, is it about any diameter? It's going to be about a cylinder axis, because what you're doing here, if you think about the rotation, you're not. I guess if we look at it one more time, about any diameter. Let me show you the notes. That might make a little more sense. I think I'll probably just wind up just giving you the inertial formula next to the problem, so you don't have to worry about that. Because I think that can be a little dicey. But if we click on, I think dynamics, yeah. So you kind of see the rotation. You know, it's rotating like this, and there's the axis right there. If it's rotating about a diameter, yeah, I guess you would think of the hoop kind of just sort of just spinning along its diameter. So like if I kind of if you kind of focus on my camera, I don't have any. Okay, I should have become a little more prepared, but like I have my planner here, right? So it would be kind of spinning like this if it's going about its diameter. Imagine this sort of hoop. It's not a hoop box, it's a rectangle. But if it's rotating about cylinder axis, kind of doing this, which is what we're dealing with, right? We're dealing with this kind of motion, not this motion. So that's what's happening there. That's why I wouldn't use that equation. I use that equation. Hope that makes sense. But again, I think I'll just give you that I that you need for it. So it's going to be mr squared. And we already have the mass and the radius. And then you just work it out, and you should get their angular momentum. So that should be pretty straightforward. For 3, and again, I think 2 is a really good final exam problem. I like that problem a lot. A wrench is used to tighten a nut. A 10-Newton force is applied 20 centimeters from the axis of rotation. What does a torque do? Okay, well, we talked about torque. Torque is just force times radius. I guess we assume it's going at a 90-degree angle. We should have been told that. But I guess if you're not told, you assume it's 90 degrees. Sine 90 is 1, so don't worry about it. So it's 10 times 0.2. Remember, you got to change that to centimeters and meters. So you should do 0.2. 4 straight up. A string is tied to a doorknob 0.9 meters from the hinge. So it looks like we have a diagram, which is awesome. At the instant shown, the force applied to the string is 50 newtons. What is the torque on the door? Well, your radius is obviously 0.9, and the tricky, and of course the force we're applying is 50 newtons. The tricky part is knowing what angle to use. And notice they put 15 and 75. So you're always gonna, so this is the force you're applying, right? And you want the force to be, it's a little tricky here, and you can go about this a couple ways. You want your force to be perpendicular to the radius or to the lever arm. That's how torque is always applied. So you always want this. That's really the force we want, the perpendicular force. Now, if you do 15 degrees, that's obviously going to be 15 degrees because that was 75. And your force here is 50. So I'm going to wind up using a cosine. So my force perpendicular, which is this right here, cosine 15 degrees equals F perpendicular over 50. And so then F perpendicular will be 50 times cosine 15 degrees. Now, if you so desire, you could wind up using 75 degrees. 75 degrees right here. Okay, that's really messed up. It was just awful. I could do better than that. In that case, you're using a sine. So it's a little tricky there. You can see what they did in the answer key. They did sine. Just, you know, sine 75 and cosine 15 are identical. That's a trig identity, which those who just finished Algebra 2 obviously haven't seen that. You'll learn about that in the fall. Yeah. Anyway, sine 75 equals cosine 15. Excuse me. So that's what's happening there at that one. But another thing to think about, hold on a sec here. Is that you know, you tend to use sine for that kind of stuff, but anyway, not sure if I'll do one quite like that because that one might be a little confusing. We'll keep moving. For 5, we've done these kind of problems before with a seesaw. 4.7 kilogram ball, 1.2 kilogram ball, and you need to figure out where to place them. So you need the torques to balance. So remember, torque is going to be F times R. And obviously, the weight of each of these are going to be strictly perpendicular to your lever arm. So this is your force, your weight due to gravity. And this is your lever arm, which is the balance beam, I guess, whatever you want to call it. So you don't have to worry about angles at all, but you do need the torques to balance out. So whatever torque this is, has to go that torque on the other side. And they want you to balance it, right? So you guys work through that one. 6 is more the same thing. Meter stick is pivoted at the 0.5 meter line. A 5 kilogram object hung in the 0.1 meter line. So where should the 8 kilogram object be placed to keep it balanced? So you do have like a meter stick, right? And you place the fulcrum there. And a 5 kilogram mass, so if that's a 0.1 mark, obviously this is the 0.5 millimeter mark, duh. And here's your 5 kilogram mass hanging right there. So where do you place 8 kilogram mass, right? 7. Marshall wants to remove a tree stump from the ground. To do this, he puts one of the long beam under the stump. It's all his weight on the other end. His weight is just enough to lift the stump. The stump weighs 5 newtons. Marshall weighs 150. What is mechanical advantage? We have to talk about mechanical advantage. Mechanical advantage is right here. It's your output force divided by your input force, and your input lever over your output lever. I use, I think, Ri over Ro, same thing. But L stands for the length of the lever. So yeah, in that case, you guys should be okay with that because you'll definitely know the both forces. So you can kind of work that out. That's not too hard there. System pulleys allows mechanical lift. Allows mechanical lift a 5 Newton engine. The mechanical lift engine with a mechanical advantage of 4. That's gonna be easy. Just use that formula again over here for mechanical advantage. 9, during a spin drive cycle, washing machine motor slows from 100 rads to 10 rads, while turn a drum through an angle of 90 radians. So that's going to be your angular displacement, 90 radians. What is maximum angular acceleration? Well, obviously you have kinematic formulas for rotation. We want the angular acceleration. You have your initial and final omegas, and you have your angular displacement. So you use this formula right here. So again, use these formulas. The formula sheet's your best friend here. And time was irrelevant, so you knew not to use one involved time, and of course you want acceleration, angular acceleration, mind you. A wheel originally rotating 10 rads per second undergoes constant acceleration. What's the angular speed? So you use the same formula again. Same thing right here. So you should be fine for that one. For 11, a grindstone is at rest given a constant acceleration, so it makes 5 revolutions in the first 10 seconds. What is this angular? So your initial angular speed was 0. And you do have the time. So, and you want to make 5 revolutions in the first 10 seconds. So if you're doing 5 revolutions, you can get the angular displacement. Just so you know, 1 revolution is 2 pi radians, right? 1 rev is 2 pi rads. So 5 revs proportionally would be 10 pi rads. And you're given initial is 0. You want angular acceleration, you have time, and now you have your displacement. You're going to be using this formula. You have your displacement, which is 10 pi rads. Initial velocity is 0, that goes away, that term. 1/2 alpha t, you know t is 10. So that's how you do that one. I think all these are great final exam problems, 9, 10, 11. I like any of those 3. Those are good ones. Mechanical advantage, I think, is a little too easy. We didn't really talk much about that. I do like the balancing ones. I think these are good too. And just so you know, most likely I'm actually going to write it tonight, the final. Well, I have to write tonight, obviously. When I do the multiple choice portion, 25 questions, we've had, it's fair to say about 6 units. I know circuits and waves probably not have emphasized as much, but I think what I'll probably wind up doing is I'll most likely pick a couple of questions that deal with or maybe a couple questions that deal with circuits and a couple with waves. So maybe about 5 questions total will deal with waves and circuits. So if you think about it, we've had 5 weeks of material, right? So naturally I should do 5 questions per week. So waves and circuits, again, maybe 2 or 3 questions on waves, 2 or 3 questions on circuits. This stuff will probably put 5 questions on rotational motion. Then I'll put 5 with kinematics, 5 with force, and 5 with energy/momentum. So if you think about this, I definitely like number 2 for sure. I definitely like something like 5 or 6. I definitely like something like 9, 10, 11. So that's 3 questions right there. I'm probably going to ask. I'll probably just wind up just doing something similar and just putting it in there. Let's keep moving to see if there's others that I might like. But again, 11, you're going to be using this formula here. Let's take a look at 12. The string is wrapped around a pulley of radius 1 meter and a moment of inertia of that. If the string is pulled with the force of F, the resulting acceleration of the pulley is 50 rads. We haven't really done that. I don't think that's really an appropriate problem for us. So yeah, because we haven't really talked much about pulleys. I mean, if you look at the formulas, I suppose. Yeah, let's cross off 12. So if you printed this, or if you're taking notes, just cross off 12, because we haven't really done that. Let's look at 13, however. So for 13, so certain merry-go-round is accelerated uniformly from rest to that at that rate. So you have the acceleration, you have the initial angular speed, you have the time. If the net applied torque is 600 Newton times meters, was a moment of inertia of the merry-go-round. Well, we know that torque equals I alpha. So that's one formula, but also we know that, hold on, where the heck is it? Yeah, we know that torque also equals the change in momentum over change in time. That's another formula, but yeah, I don't know why it's not here, because we have, this is on the previous page. That's strange. Yeah, because I know we totally have done that. You may, that's network. I mean, I guess you could, yeah, there it is. Okay, I'm losing my mind. Net torque, I alpha, yes, we have talked about that. So yeah, that's a fair problem, because we have talked about torque being I alpha, and you have your alpha, obviously, is 10, and you want the inertia. So yeah, so the rest of the stuff actually was kind of useless. You didn't even really need the 30 seconds. You have the acceleration. I think what I probably would do is I'd probably make you find the acceleration and then plug into the I alpha formula and then solve for I. But again, torque, which is given to you, equals I, which is what we're trying to find, times alpha, which is given right there. So perhaps the answer is going to be 60 for that one. For 14, a 100 kilogram rider on a moped of mass 8 kilograms is traveling at a speed of 20 meters per second. Each of the two wheels of the moped has a radius of 1 and a moment of inertia of 2 with a total rotational. I like that one. Rotational kinetic energy we know is 1/2 I omega squared. And you have the inertia, so you don't have to worry about that. But you will need to figure out what omega is. And if you already have the speed, so yeah, just you got your I, so that should be pretty easy. So some of the other stuff here actually was a little bit useless, like 8 kilograms 1 meter, 100 kilogram rider, a lot of that was actually useless information. So you could filter that out. Again, I think the way I would design this one compared to 13 is I'd probably make you find what the omegas, or maybe I might say a, and by the way, that's speed. So V equals omega R. So 20 equals omega times 1, but omega is still 20. You could do, maybe I could ask like what's the total kinetic energy, rotational and translational, because then if you have the mass and the speed, you could do the total kinetic energy as well. I think I'll probably do something with conservation, however. So I told you I didn't like 12, but I did like problems like 9, 10, I did like the balancing, I did like some like number 2. I like, you know, something like 13 or 14 involving torque. 15 I like a lot. That's gonna be conservation, and you'll see why in just a sec. But let's look at 15. Sorry, 16 I like a lot. 15, the wrench uses a tie and a nut as shown in the figure. So you have the lever arms 5.1 meters, and then you're applying a force that's perpendicular going downward. 100 Newton force applied, 10 centimeters an axis of rotation. Well, that's not consistent from what we see here. Hold on. What is the work done to turn the nut through 1.5? That's really interesting. The diagram does not match with this information here. So this diagram is actually off. So yeah, so your work is right here, tau times theta. So we know force times radius is going to be our torque. But also, so you could do that, that's 100 times 0.1. And then you're rotating angle 1.5. So again, it's I omega there for that one. And then I like 16 a lot. That's a good one. 5 kilogram solid sphere. So you know it's a solid sphere. So now you know which inertial form you're going to use. Solid cylinders is mr squared over 2. Again, I'll tell you what inertial form to use, so you don't have to worry about that. Rolls down a 5-meter hill, starting from rest. What is the final velocity of the sphere at the bottom of the hill? So what you're going to have to do is set up your so we have that. Initially, we know both these are 0. And that's going to be 0 right there. And we know that this is mgh. And we know this is 1/2. And it's 1/2 I omega squared. And I is going to be, going back to our formulas again, is mr squared over 2. So yeah, I have my mass, I have my radius, I can get the inertia, that's easy. Again, I could plug in mass here, I could plug in mass here, plug in height here, plug in g there. Omega is, so remember V is omega times R. We know this, right? So you can actually replace omega with V over R. and R is 1, that makes our life a little easier. And then substitute that in for omega over here. And that just becomes v squared. Then your goal is to solve for velocity. I like 16 a lot. So just to kind of make a little, some notes here, what to expect for our final. I definitely like something like number 2, something like 5 or 6, something like 9, 10, or 11, something like 13, probably somewhere like 13, because we should have something that does involve torque, I suppose. I mean, you could say 14 also, but kind of like 13 a little better, and I like 16.
Mr. Amashi, for the test, I feel like if there's like 5 of those problems from one unit, it would take like I don't know if I could do that like 25 times in 90 minutes.
Well, the other question is going to be faster though.
All right.
Yeah.
Would you do like 1 or 2 of these questions out of the 5 and then have like other stuff, or like it would? Because I've been taking like 2 hours on like.
I think what I could is I could increase the time for the final. I could do that. As you know, I've been pretty lax about that. I do think 16, yes, that would take a little time. I would agree. But also I do feel something like 12 would be pretty quick, because you do have a formula there for that. I do think, or maybe what I will do, you know what? Because I should ask at least 1 or 2 conceptual questions. So you do make a good point, Isaac. So maybe what I think what I'll do is I'll probably have like maybe 2 more just conceptual questions about the stuff, and then probably maybe I'm getting a little too ambitious, and maybe just 3 calculation problems. But I do like 16 a lot for sure, and I am definitely a fan of 9, 10, 11, and I kind of like 2 or 5, 6. I could probably have something that's a little more conceptual, maybe regarding those other problems. So, but you do bring a good point, and I'll kind of go through this exercise of like what problems I want to assign for the other 3 units we did yesterday. Because I know I didn't quite do that. But anyway, I think now it's time for you guys to do some practice. So I'm gonna have you guys work through pretty much all these problems, 2 through 16. Work through them. I'll give you guys about 35 minutes or so. We'll come back around 11:20. No, 30 minutes actually, because I want to come back at 11:20. Give you guys enough time to ask questions if you're stuck on it. And of course, call me into your rooms if you're stuck. We'll go to breakout rooms right now. We'll come back. We'll spend a few minutes seeing if there are any questions. Then what we'll do is after lunch break, we'll do waves is really short, and circuits are really short. And then near the end of class, we'll kind of go back to the units we talked about yesterday and talk about what questions I think I'll ask in the final. Another thing I could probably potentially do too is I could probably put more calculation-based questions in the lab practical. So that's another thing I could do as well. So, and obviously I gotta create that too. So I got my work cut out for me tonight. Probably won't sleep much, is my guess. Okay, so let me stop sharing.